Okay, so we just finished electrical energy, and the question just came up: does the size of the wire matter? And yeah, it does. So a bigger copper wire is going to have less resistance than a small one. And let me just take a moment to show you the relationship there. So, and I don't want to beleaguer this, but if I've got a copper wire, and I'm just going to do this really quickly because I do want to move on, but it's certainly worth mentioning as it will come up later. If this is just a copper wire, it's going to have some length, and it's going to have some area. Now, obviously, the longer the thing gets, the more resistance it's going to have. The fatter it gets, the less resistance it's going to have. So here's a good opportunity to look at the difference between an intensive property and an extensive property. So the relationship is that the resistance equals what's called the resistivity. Now, that symbol that I just wrote is the symbol rho. It looks like a P. It's the exact same symbol that I used to define density a second ago. And in a sense, it's very similar to density. It's how much resistance there is per unit copper, just like how much matter there is per unit volume for material density. So to get resistance from resistivity, the longer it is, the more resistance there is. The fatter it is, the less resistance it is. So, and you will use this in your 243 PV course. This is very important in terms of looking at electrical losses. This is why you're always weighing, do I want to use a short fat cable or a long skinny one? And usually the shorter and fatter the better. But then you have to weigh that against cost too. So, the upfront cost in terms of reducing resistance versus the long-term cost.
So you define the resistivity if you already knew what the resistance was, if you measured the resistance?
You could, yeah. If you were a scientist in the lab and you had a brand new material you're trying to find the resistivity of, that's exactly what you do. You'd measure the resistance, you'd measure the length, you'd measure the area, and then you get the resistivity. Perfect, yeah. And that's the fundamental difference too between science and technology. The technologist is working with the equation shown here. The scientist has the rho on the other side of the equation. Yeah, that's a good question. Okay, so let's pop on out to electromagnetic radiation. So 4.5 EM radiation. Why is it called electromagnetic radiation? Well, it's because electricity and magnetism are fundamentally related, and I think the individuals responsible for that are shown here. Too far ahead of myself. Oh, there's your electrical circuit, pretty simple. There's your V equals IR, obviously very simple. You're doing that every day in 105, don't need to cover it here. A battery, voltage between the two terminals that's equivalent to force, and current obviously flowing through is the same as current water flowing. And then, there we go. Yeah, so there's Faraday, and then finally here is Maxwell. So Faraday was quite a good experimentalist, but he did not have the mathematical tools at his disposal. So he knew that electricity and magnetism were related in terms of when a magnet moves, electricity flows. If you can get electricity flowing, you can get a magnet to move. So he knew that they were fundamentally related. James Clerk Maxwell, who's shown here, was quite well educated in the conventional sense, had the mathematics at his disposal, and I'm just going to show it to you briefly, and you will not be expected to know this, but I just want to show you more or less what Maxwell's breakthrough was, because there are four equations. So here's your electric field, here's your magnetic field. Faraday knew the two were related. So did Ampere, so did Gauss. And so I'm going to make this a little bit smaller. And again, what Maxwell was able to do was to show, so this is just Gauss's law showing that more or less, and this is another form of the first law of thermodynamics, showing that electric charge is neither created nor destroyed. If it goes away somewhere, it's going to come back somewhere else. That's that. Same thing with magnetism. Magnetic fields, they might reappear and disappear, but they're always also conservative. You're never going to get energy out of a magnetic field, just like you're never going to get energy out of a gravitational field unless you put it in. You're never going to get energy out of a spring either unless you put it in. Magnetic fields behave the same exact way that gravitational fields and springs do. So that's, you can think of this like your conservation law. Now, he showed that when a magnetic field changes, that's just those little D's are just small deltas like we showed with delta temperature. When that magnetic field changes, so does the electric current. This stuff out here in front just shows that they're perpendicular to each other. And when we take a look at the electromagnetic waves of light, you'll see that perpendicularity. You've seen polarized light before, so you know that light can be polarized. It's got a direction. And then this one finally is more or less, again, this equation just in reverse, more or less. It's just showing when the electrical field changes, so does the magnetic field. So Faraday sort of knew this intuitively. He was doing experiments. Maxwell came along and put them all together into one set. Okay, so there's Maxwell. And I certainly want to show you Planck as well. So electromagnetic radiation, I think we talked a little bit, we talk about this in more detail in 102, but the sun emits at really all of these frequencies. In fact, in a sense, everything emits at all these frequencies. It just so happens that our particular sun, our star, emits primarily in the light band. That's the one we can actually see here. The rest of these are obviously invisible to our eyes, but we use them all the time. So here's microwave as an example for how our cell phones work. Here's TV up in the UHF, or ultra high frequencies, very high frequencies, shortwave, et cetera, et cetera. X-rays are down here. And what I think you can probably see, well, I guess it's not exactly given here, we can tie these frequencies and wavelengths directly to energy. So if you know the wavelength or the frequency of a light wave or a photon, either way you want to think about it, doesn't matter, you can say precisely how much energy that photon has. Okay. And the reason is because this guy sat down and thought about it for a long time. In some of the initial physics experiments, when very low light levels were used, so, rather than sort of like a hum coming through the circuitry, it was more like a little pop. Every time a single photon. So it became very apparent to some of these early physicists that matter and even light is in fact discrete. It's in little tiny chunks. Just like when we were looking at the periodic table the other day. There's just a certain number of protons in an atom, a certain number of electrons in an atom. Same thing is true of light. So let me just do one quick little equation to show you that. We'll go back to that figure with all the frequencies on it, and let's look up Planck's constant. You will not need to know this when you're installing a PV panel. No one's going to say, how many photons am I getting here? But on the other hand, when we start to look at the physics of PV cells, you you might find yourself in a photovoltaic manufacturing plant. It's going to be handy to know some of this stuff in terms of what a photon will do to an atom when it comes in. Okay, now we've already talked briefly today. We reviewed what the dimensions of energy are. Can we now figure out, using what we know about dimensions, how much energy is in a single photon using Planck's constant? So let's write this down. 6.62 Planck. 6.62 times 10 to the negative 34. Negative 34. Meters squared, kilograms. You know, I'd say, why is there a kilogram floating around in a photon equation? But there it is, per second. Okay. All right. So what's missing from this thing? What's missing from this thing to actually make it look like energy? So, because the kilograms are mass, the meters squared are length squared. What's missing from this thing to actually have it just be energy? I'm missing one time in the denominator. So another way to look at this is, well, another way to look at it is the fact that a kilogram meters squared per second is in fact 1 joule. So another way to write this, it's going to sound kind of funny, but this actually equals 6.62 times 10 to the negative 34th joule seconds. Remember when we did kilowatt hours a while back? That was, did I do that right? Hang on one second. Let me back up. Joule seconds. Joule seconds. Yeah, that's correct, because I multiplied by time. Yep, and it's confusing. Sorry. Kilowatt. Yeah, right. Okay. So unlike the exercise we did previously, where we had kilowatts times hours, or power times time to get energy, it's similar but different. Okay, and what I mean by that is, if we go back to this figure, and let's just go in here and dig out something. So here's light, and let's just say I've got a photon of light that's at 10 to the 15th hertz. So what that means, and you guys are familiar with a hertz, right? So a hertz is 1 cycle per second. What this means is this photon is essentially vibrating 10 to the 15th times per second. Way down here, well, these are still in the order of 10,000 hertz, but the photon is vibrating very quickly is the upshot of that. So 10 to the 15th hertz. What are the dimensions or the units of hertz? It's just 1 over time. It's frequency. So now I think you can see, or 1 over seconds. I think you can see that if I multiply hertz by Planck's constant, energy is going to come out. So back to what I was saying, if I know the frequency of that photon, I know how much energy it has. And therefore I know how much energy I can push through my photovoltaic array, or really how much energy my solar thermal unit can absorb. And it's tiny, but it's fun to calculate. Okay, so for light, we're gonna say that the frequency equals 10 to the 15th hertz, or 1 over seconds. So now here comes the upshot. the energy equals Planck's constant, which is given as a symbol h, times the frequency. In this case, we're just taking 6.62 times 10 to the minus 34ths joule seconds times 10 to the 15th hertz, or 1 over seconds. So right away you can see, okay, joules are going to come out. That's what we wanted. That's what we wanted in the first place. And I'll break out Microsoft Excel to do this one. Okay, so I'll just do it straight away. Equals 6.62 E minus 34 times 1 E 15. Okay, 6.62 times 10 to the 19th. Well, in fact, we could have just done that in our head. It's 34, or negative 34 plus 15. So I'll write that up here. Sorry, I kind of ran out of room. Equals 6.62 times 10 to the minus 19 joules. So what that means is I need approximately 10 to the 19th joules, or photons at that color, just to make 1 joule. So it gives you an appreciation of just how small and invisible, or like paradoxically invisible photons are. Okay. All right, so there's a little electromagnetic radiation. We covered Planck, we covered Maxwell, we looked at the full electromagnetic spectrum. There is just a little PV charger, little PV cell, photons streaming in and turning into volts, and we'll get into that in more detail in 102. I'm sure you've also started talking about series and parallel in DC, so all of these guys right here are in series. And I think you can also see why if one part of the panel is shaded, it more or less becomes a resistor, it becomes a liability, and all these photons end up kind of flowing into it and really messing up the circuit. So that's another good analogy for this. I guess another good analogy is locking the bullpen. If one of the padlocks is out of place, the whole thing's screwed up. So this is the importance of having a knowledge of series and parallel. And this 0.5 volts is pretty standard for most little PV cells. And in order to get enough voltage to the point where you can actually do something valuable, you have to put them in series, so that voltage adds up and you get enough force. Pushing force. Okay. Well, let's keep cruising here. We got about 20 more minutes. I want to cover chemical energy. Chemical energy does not lend itself quite as well to the mass, length, and time that we've covered previously. I will hop back out, though, to the dynamic periodic table, because it will inform us. If I'm not mistaken, there used to be, oh, here we go, electronegativities. So for each atom in the periodic table, the electronegativity is more or less telling us how, on a relative scale, how tightly or untightly the electrons are bound to the particular element. First off, you'll notice the noble gases have 0 electronegativity. They're at their lowest possible state. Helium and neon, if we were looking at the orbitals, we would see that they're full. The values. Okay, so as we sort of click through, Lithium, relatively high electronegativity, good for batteries. Where's lead? PB must be down here somewhere. 82, okay, yeah, thanks. Lead, pretty high electronegativity, 2.23 in comparison to some of the neighbors. And the chemistry does get fairly complicated, but it's more or less the relative electronegativity of the elements that allows electrons to flow through chemical circuits, a battery being a perfect example of a chemical circuit. Okay. Next things that the other things that are mentioned here in the text. Let's get into this. Is the so 4.6 chemical. So we looked at electronegativity. The next thing I want to look at is the energy density. So the second little blurb in here says using chemical energy. So let's look at energy density really quickly. This also comes into play in designing your energy technologies. So let's pop out here to energy density. There's a really neat table that I refer to frequently. If you scroll down here, energy density. Obviously, the units are in joules per cubic meter. You probably recognize that from summary number 1. And you guys can see that fairly well. You can measure energy density on 2 different scales. One is energy per unit mass, that's megajoules per kilogram. The other one is energy per volume, or megajoules per liter. So most of these reactions, well, they're varied. In the case of the lithium-ion battery and the zinc-air battery, those are based on the relative electronegativities of the compounds involved. These guys up here, ethanol, gasohol, butane, kerosene, et cetera, those energy densities are more or less based on combustion. I don't know if coal is on here anywhere. Do you guys see? You see coal? I think coal might be.
Anthracite.
Oh, okay.
One of the top 3.
Oh, there we go. Yeah, super. So, energy. So in this case, really high energy density per unit volume, relatively low per unit mass, but it's more or less right in there with ethanol. The reason I thought coal might not be on here is because there are different grades of coal, and anthracite's one of the higher grades.
So bituminous is directly below that in the center of all of it.
Oh, is it really? Oh, good eye. Oh, thank you. Yeah, there we go. Perfect. Yeah. So those are 2 separate classes of coal that obviously different energy densities. Perfect. Way out here is hydrogen, and you can see it's got a fantastic energy density per unit mass, but very low on a per volume basis. That's why our hydrogen truck, for example, has to store it at such high compression ratios to be viable. Okay, so this is more or less a chemical energy density plot. Periodic table, atomic number, syllable. So table 4.1 more or less lays out the periodic table, but just in alphabetical order. Here's your methane molecule. We looked at the periodic table before. We know that carbon, let's So it's kind of a neat place. Maybe I'll go back there. So there's carbon again. If we look at the orbitals, we can again see that 2p shell is more or less missing 4 of its 6 electrons. So if I head over here, it's missing a down electron there, a down electron there, and an up and a down. So there's the logic behind looking at that methane molecule just like so. Hydrogen, obviously, right here with that single electron. So that single electron sitting there in hydrogen binds in those 4 openings in carbon. So that's how to tie the periodic table together with this cute little figure of a methane molecule. Okay, when methane burns, so here comes your oxygen. When methane burns, what you're left over with is well, a CO2 molecule right there. So this is a fantastic graphic. You can see that little carbon atom just comes right through, takes its place right in between those 2 oxygen atoms. Boom, there it is. And then these 2 oxygens more or less suck up the hydrogens off of that methane. So you've got a single CO2 and 2 waters coming off of methane combustion. And so a lot of times when people say, oh, well, methane's a cleaner fuel than coal, than oil, this is the reason. There's not sulfur in there. The chemistry is very simple, easier to control in a sense. So when you hear that, you know, methane or natural gas is cleaner, this is what's being referred to. And then looking there at box 4.10, table 4.2, you can see that the heating values of coal, oil, methane, etc. are given. The value given for coal is 28 megajoules per kilogram. Let's see how that compares to the website we were just viewing. Let's go down here. What did I say? 28. So the book says 28 megajoules per kilogram. Let's go back down. And the book just gives it as coal. 28 megajoules. Yeah, so call that about right. It's actually a little higher. I mean, so it's kind of right between bituminous and anthracite. I'd put anthracite north of 30 and bituminous more 25-ish. So it's kind of a ballpark average, 28 megajoules per kilogram. A couple other things worth mentioning are the lower heating value versus the higher heating value. The difference between those two, in the lower heating value, it assumes that all of the energy from your combustion, if you're heating water, all of that water just leaves the system, and all of that heat leaves the system. So you can just kind of think of this as H2O leaving the system. The higher heating value, what you're doing, and this would be more in a power plant, the H2O actually comes back, and that heat is recovered in a heat exchanger. That's the difference between the lower heating value and the higher heating value. When you see those two acronyms there in table 4.2, that's all that means. And so the higher heating value will always be higher because you didn't lose that heat from the water just sort of saying, see you later. You got it back into your system. And this is also a big deal now in some, they're called condensing boilers on houses. You've probably heard the word condensing boilers. Are more efficient because that water actually condenses in the exhaust gas and comes back into the house rather than just, hey, see you later, don't need you. So higher efficiencies. You're closer to that higher heating value.
What was that
heated water, how's that dealt with then when it comes back?
You know,
They just pump it back in and let it,
yeah, it's
almost
good.
like a in-floor heating kind of thing, where it just kind of like puts itself down.
Yeah, I'm sure there's various ways.
Well, it goes through a condensing coil, that's how they get it to condense.
Yeah,
And it
but
captures that heat to lower the temperature back down to the water from a vapor to a liquid.
that condensed water, though, does it end up? I mean, it.
I don't know.
I'm sure there's some open system, some closed system.
Sewer system, yeah.
They've taken the energy out in that condensing coil. They don't really care about the water itself. It can go wherever.
Yeah, I'm sure there's various ways to deal with it.
I'll tell you, Troy captures his in his system,
Mm-hmm.
and he uses it, and it's basically distilled water at that point.
I use it for water.
And they have a bed and breakfast, and they use it for like ironing their sheets and stuff.
Oh, nice.
Water.
Nice.
So it doesn't flow stuff up.
Okay, so we got one last little bit to cover, and then we're done with chapter 4. And that is the nuclear atom. So up to now, the only thing we've been sort of playing around with are chunks of mass flying around, electrons flowing through wires. We've looked at some electron exchange, obviously, when methane is combusted. Now, what we're looking at, so this is Ernest Rutherford, large, exuberant man, attracting lively groups of students and co-workers. But he was sort of famous for discovering the nucleus, more or less. You know, firing things through very small films and realizing sometimes things get deflected or bounce back because they're actually, well, there's a lot of empty space inside the atoms, but there's also the nucleus itself.
No beard though. How famous could he be?
No beard? Yeah, gosh, yeah. Little mustache, though. Entering the modern era. So this is just kind of a cartoonish depiction showing protons and neutrons inside the nucleus of the atom, also showing that it is in fact positive. So the protons in red are positive, the neutrons are negative. We'll talk in a little more detail later when we get to nuclear energy, kind of, you know, what holds the nucleus together, etc. But the electrons themselves are attracted to the nucleus because they're negatively charged. And it's essentially the mass number that determines it's just the mass number that determines the atomic number. So boron, for example, has 5 protons in its nucleus. 5 for boron, 6 for carbon, 7 for nitrogen, etc. Also worth noting that carbon, fundamentally, to be carbon, has to have 1, 2, 3, 4, 5, 6 protons in its nucleus, and a typical carbon, the most plentiful carbon, it also has 6 neutrons. Well, you can add an additional neutron. It's still carbon because it's still got the 6 protons, but it's carbon-13 and is radioactively unstable, and it's this that's frequently used, this carbon-13 and carbon-14 that are used for carbon dating. Okay. Now, the final equation that I want to share with you before we adjourn here is that E equals mc squared. So that's Einstein's equation. I think there's a shot of him in here too. There he is. And hopefully by now, with the units and the dimensions that we've been covering, we can see that obviously the dimensions of m are just mass. What are the dimensions of the speed of light? Just like any other speed. Distance per time, yep. Distance per time, and then we can finally see that it's just, so the dimensions, that's what I mean when I put these little brackets around it, the dimensions of energy are just mass times length squared over time squared. And this is not something we typically, deal with. These are very high energies, but for example, and I was just reading about this the other day, in the Hiroshima bomb, I think it was 67 terajoules of energy released. So from that, and knowing the speed of light, we're kind of out of time here, so I'm not going to run the equation, but knowing this and knowing the speed of light to be, 300 million meters per second, you can then find out more or less how much matter during that nuclear explosion turned directly into energy. Well, what kind of energy? Heat, radiation, kinetic, etc. That's kind of where it went. And again, a demonstration of the first law of thermodynamics, that you cannot create it or destroy it, just change its form. So, all right. Well, that's it for chapter 4, and it's kind of a whirlwind tour of all the different energy types that we're going to cover in the rest of the book. So, remember that 10 megajoules? Pretty easy to remember. Be a good idea to kind of keep in the back of your mind what the density of air is, what the density of water is. What are a couple other good kind of...
Watts per meter squared. So
watts per meter squared is another good one. Just keep that 1,000 watts per meter squared in mind. Don't forget your power equation. Just always remember that energy is power times time. I know I kind of threw a lot of stuff at you today, but when it all boils down, if you can just remember those few fundamental things, you can derive most of the rest of this stuff. So that's and hopefully what I've impressed upon you is every one of these guys. Well, this is 4.7. Every one of these little sections. This is 4.7. Oh yeah, 4.7. Beyond chemistry. It's not called nuclear. It's just beyond chemistry. Beyond chemistry. Obviously, the unifying theme here in all of them is just energy. We've started out with heat. We moved on to electricity. We tied those two together. We even looked at kind of a power bill scenario. We tied heat and electricity together right here. That's how we did it. Unified those two things. Even took a little tour down resistance lane. That was fun. Did electromagnetic radiation. Again, energy ties it together. Chemical energy. Looked at batteries versus combustion. And then finally did a little Einstein to wrap it up. So thanks everybody, and if you can stick around to put up the wind turbine, that's little human power into kinetic, into electric, into chemical.
That's something to think about for Tuesday morning. Just not real in depth or anything.